Okay, example 4, we're going to do a cylinder using the divergence theorem. Again, we're going to do the divergence theorem first here, and then we'll show that the surface integral gives us the same thing. We have done cylinders several times already with surface integrals, but we'll still show it because this one has a radius here of a instead of an actual number. So basically what we're looking at is we have this cylinder, something like that, where the radius up here is a units long. All right, so let's do the divergence theorem. So let's figure out what the divergence of f is. Well, the divergence is the partial of the first one with respect to x, that's 1, plus the partial of the second component with respect to y, that's 1, plus the partial of the third component with respect to z, that's 1. So our divergence is simply 3. This is a cylinder. It doesn't really make any sense to do this in anything other than cylindrical for the divergence. So let's go ahead and write it in cylindrical terms. So we're going to have our flux will be the triple integral of 3. And since it's cylindrical, it will be r dz dr d theta. Okay, and we needed to put that extra r in there because that is a part of the cylindrical. So let's see. I don't think it's going to matter which order we do this in. Let's just go ahead and do the z part first, since that's the order I wrote it in. So -1 to 1 is z. That's defined right there. R is going to go from 0 to a. 0 to a. And then theta, of course, goes all the way around the circle. So that's 0 to 2 pi. So let's go ahead and split this one up. So we've got 0 to 2 pi of d theta times 0 to a of r dr and -1 to 1 of dz. Let's just put that 3 out in the front there. It's a constant. So the first one is going to give us 2 pi. The second one is going to give us 1/2 r squared from 0 to a. And the last piece is just going to give us, it's a constant, so it'll go from -1 to 1, so that's just going to be 2. So the only one that we actually have to do a little bit of work on here is that the second integral. So we're going to get 2 times 2 pi times 3 is 4 pi, 12 pi, times, plugging in a, you get a squared over 2. Plugging in 0, you get nothing. So it looks like we are going to get 12 over 2 is 6. So we're going to get 6 pi a squared. Again, very, very easy to do the flux of this particular piece. Now let's go ahead and show the surface integral. Again, this is something that we have done, or at least the parameterizations we've definitely done. So let's go ahead. We have to split this up. We have 3 pieces. We have a top, a bottom, and then the lateral face. So let's do the top first. Doesn't really matter, it's just the one I picked. Again, I'm going to go ahead and parameterize this in trivial at this point, because it's just the top disk. So x is x, y is y, and z has to be 1 because that's the top bound for z right there. So if I parameterize it, Rx is going to be 1, 0, 0. Ry is going to be 0, 1, 0. We've seen this several times before. So we're going to have Rx cross Ry. The first component here is going to be 0. The second component is also 0. And the last component is 1. That's perfect. It should be facing straight up. We should have expected it to be 0, 0, 1 in this case. Let's go ahead and parameterize our f. F is just x, y, z. So literally that's what we're going to get. X, y, z. I didn't really care about the first 2 components. I just wrote them in because when we dot these 2 things, remember this is your normal. Remember, when we dot these 2 things, the first 2 components are going to go away. So really, you're just going to get z for your dot product. So we're going to go ahead and take the double integral of z. Did I do that right? Oh, well, that's true. Yes, I did do that right, but z is 1. So I probably should have just put a 1 in there. Let me go ahead and fix that. That's a 1, because that's the value of z in this case. So we're going to get 1 dA. Well, now once again, I have a double integral of 1 dA. That is just the area of the domain. But this thing is a disk. It's just the area of that circle with a radius of a. So the area of a circle, of course, is pi r squared. And r here happens to be a, so this is going to be pi a squared. Again, you can go through the process. You can put the 0 to a and the 0 to 2 pi of r d theta, and you will get exactly this, pi a squared. Okay, let's go ahead and do the bottom. Okay, same exact idea. X is x, y is y, and in this case z was, I believe it was -1, correct? Yeah, -1. There's -1. I am not going to go through the cross. We should know this is the bottom disk. The z component should be facing straight down. So our normal vector here, or the cross product, should be 0, 0, -1. Okay, if we parameterize it, we're going to get, really it doesn't matter here, but I'll put the x, doesn't matter there, but I'll put the y, and then z, but z in this case is -1. So the dot product is 0 plus 0, and then -1 times -1 is +1. So once again, we simply get the double integral of 1 dA, which is just the area of the bottom disk. Well, it happens to be exactly the same thing as the area of the top disk. Again, I hope you're following all that. Now let's go ahead and do the lateral face. Well, we know we have pi a squared. We know we've got another pi a squared, so that's 2 of them. The lateral face should give us 4 pi a squared, but let's just go ahead and show it. So the lateral face. Now in this case, I'm going to go ahead and parameterize this one in cylindrical, because now we're actually talking about just the outside ring. You could still do this in trivial and then change it to cylindrical later. It doesn't really matter. I'm going to go ahead and do it in cylindrical. So I know that we're talking about just the outside face, so the actual value of the radius is a. Remember that a is a constant here. A cosine theta. Y is going to be a sine theta. And z here is just z. So now I have things in only terms of theta and z. So that means I need to do r sub theta and r sub z. R sub theta is going to be -a sine theta, a cosine theta, 0. R sub z, this is nice, is 0, 0, 1. All right, so now let's go ahead and do the cross. R theta cross RZ. Now in this case, because we're talking about this cylindrical part, these things need to be coming off perpendicular this way. You really shouldn't have anything for your Z, so we should have things which are outward for X and Y. So let's make sure that that's the case when we cross these. So when I take the I row and column and eliminate that, I'm going to get A cosine theta. That's a good sign. That's positive. When I eliminate the J row and column, we're going to get -a sine theta minus 0, but we change the sign, so that's a sine theta. Again, very good. This should probably give us nothing for the Z component, and it does. So there's our cross. Again, that's our normal. Let's parameterize F. And again, I believe F was just XYZ, correct? Yes, F is just XYZ. So we're parameterizing F as A cosine theta, A sine theta, Z. All right, so now when we go ahead and take our double integral, dotting these, we're going to get A squared cosine squared theta plus A squared sine squared theta plus 0, because Z times 0 is 0. All right, we parameterized this already in polar, so I don't need to put an extra r in this case there. So it's just going to be dr d theta. Okay, r here is going to go from 0 out to a. And again, remember that a is constant, so we can use that if we can separate these. And then theta goes from 0 to 2 pi. Well, I can factor the a squared out, and if I factor that out, it leaves me with a cosine squared plus sine squared, which is 1. So really, what I have here is a squared, which is a constant, integral from 0 to 2 pi of d theta times the integral from 0 to a of dr. So this is a squared, this part is 2 pi, and this part here, I'll write it out, is going to be the integral from r from 0 to a. So here we're going to get a squared times 2 pi times a. What's wrong with that? Something's wrong with that. What did I do wrong? Oh, my goodness. Hopefully you guys caught this a long time ago. This should not have been dr, it should have been dz. Yeah, this is with respect to z, and that's not going to be 0 to a because it is with respect to z. So let's erase those things. And that's the good thing about the divergence theorem being there, is I caught my mistake because of that. This should be dz, d theta, and z itself here went from negative 1 to 1. Negative 1 to 1 dz. So this right here is just going to be z from negative 1 to 1. And that's going to be 1 minus negative 1, which is 2. So we do get 4 pi a squared. And when you add all of those up, you do get 6 pi a squared. Sorry about that mistake. Hopefully that you guys caught it probably before I did.